Hello friends, today we will discuss the topic of no cooling in microwave mode in a microwave oven. Let's start. The customer feedback is that the microwave does not start even after selecting microwave mode button, and the convection and grill mode is working well. So microwave mode is suddenly stopped. These are the various kinds of complaints that the customer gives. The questions to be asked to the customer related to these symptoms are: was there any repair done before this complaint? To know whether any components have been replaced before, any signs of voltage fluctuations like blinking of lights observed, to confirm the condition of the supply voltage which may lead to poor microwave cooking. Did you hear any noise before or during the problem? This is asked to know whether the customer is using the right utensils during microwave mode or any electrical malfunction is there in the circuit. And the last question which you can ask is, have you tried switching off the microwave oven for a few hours and then switching it on again to confirm whether the reset is happening in the microwave controller during each switch on and off of the machine. This will confirm whether there is a malfunction in the machine. The probable defects are: the main supply voltage is less than 207 volts, that's why the microwave oven is not working. Display panel button faulty or damaged. Control PCB relay faulty. HV fuse is blown. Diode is internally short, open or faulty. HV capacitor is dry or capacitance is less. HV transformer is completely dead. The magnetron is faulty, or the customer has used wrong utensils. So the possibility of failures which we have put in a table, we have segregated into electrical, electronic, mechanical, usage and environment conditions. We will look at each of them step by step. The first thing is to check the proper supply conditions, whether the phase is to the right, the neutral is to the left, and we have got proper earthing in the 3-pin power point supply. For microwave oven, it should be at least a 16 amps 3-pin power point supply, preferably with a 16 amps MCP. And the voltage between neutral and earth should be between 1 to 3 volts and not more than 3 volts AC. And neutral and earth points should not be internally shorted. These are the basic requirements of the electrical mains plug from the customer. Here, for the first defect, if the buttons are faulty and we are not able to operate the machine, so here we can check the buttons, continuity of the buttons, by pressing the buttons and checking it on the points which are indicated in red and black over here. Across these points there should be continuity when we press the buttons. Each and every button we can check in this way. We can put the multimeter on continuity mode and check the continuity between these red and black points which are indicated in this diagram. Every individual button can be physically pressed and the continuity can be checked. This is the way of checking the button. The second check is if the touch panel is faulty. There is a printed circuit connector between the touch panel and the main PCB. In these printed circuits, the printed wires of the circuit, which are printed with carbon ink, mostly these wires, they can have a short circuit, or they must have worn off. The printing must have gone bad. So there is a problem that the display is not showing properly. It could be because of loose connection between the printed circuit and the connector. Or we can check whether due to overuse or due to misuse, any of those buttons, the touch buttons, they have got cracks on them, or there is some water which has gone inside the cracks. These are the things which can. Next diagnosis is of main PCB fault. How can we check it? The defect is that microwave mode is not working. We can check the voltage at the input terminal of the transformer after disconnecting the terminals from the HV transformer. You have to remember that we should not check the high voltage circuit when the circuit is on, or when the voltage is supplied to the circuit. We can check it only after disconnecting the input to the high voltage circuit, that the input to the transformer, and the input to the transformer can be checked by the multimeter whether the PCB is actually giving 240 volts to the input to the transformer and thereby to the high voltage circuit. But we have to remember that we should not touch the high voltage side when it is charged with voltage. We can check the input to the PCB, the red and the blue wires which are shown on this white connector. Across these two wires we should get 230 volts. This is the to the main PCB, and then from the main PCB to the HV transformer, to the primary side of the HV transformer, as shown in this picture, we have to check the 230 volt supply whether it is coming from the main PCB to the HV transformer when we are selecting the microwave mode. If the voltage is absent, that means there is a fault in the main PCB, because even though we are selecting micro mode, the main PCB is not supplying the required input voltage to the HV transformer. The second thing that we can check is the HV fuse, whether it is faulty or not. If there is a voltage coming to the transformer but in the input, but still there is no cooking in the microwave oven, the microwave mode, that means the HV fuse must have gone faulty. For this we have to completely shut down the microwave oven and wait for the capacitor to discharge automatically. It takes roughly around 25 to 30 minutes, and after that we can open this HV fuse case, and inside the HV fuse case there is an HV fuse whose continuity can be checked whether it is working or not. The equipment required for testing is a multimeter. Check the resistance, or we can check the continuity. Both of this will give equivalent results. We can also visually check through the glass tube whether the fuse is broken or whether the fuse is attached. The fuse testing mode is shown in this photo. 1.2 ohms, roughly 1 ohms is the resistance which we get across this fuse, and if the fuse is open, we get an open load indication in the multimeter. If the HV diode is faulty, because when everything else works, and if the HV diode doesn't work, still the microwave will not work in microwave function. To check the HV diode, we connect it to the multimeter and a new 9 volt battery in this way. The positive side of the battery is connected to the anode of the diode. The cathode of the diode is connected to the multimeter, and the next other end of the multimeter, that is the positive side of the multimeter, is connected to the negative side of the battery. So this completes the circuit. In this circuit, the diode is forward biased, so the multimeter should show a DC voltage of 6 volts, that is 9 volts minus the 3 voltage drop at the diode, and the multimeter will show 6 volts if the diode is okay. If it shows 0, that means the diode is internally short and the diode is faulty. And if it shows 9 volts, then also the polarity is forward bias, and then the diode is not proper. The good condition is the multimeter should show 6 volts, and if the diode is open, it will show 0 volts, and if the diode is short, the multimeter will show 9 volts. This is the proper way of checking. If we check it in reverse bias, that is, the cathode of the diode is connected to positive side of the battery and the anode of the diode is connected to the multimeter. In this reverse bias, when we check, we should get a 0 voltage, because the diode is a one-way conductor, and in the reverse direction the direct should not conduct, or it should not show any voltage across it. So a good diode will show 0 volts in the reverse bias. And if the diode is short in the reverse, it will again show 9 volts. And if it shows some other voltage other than 9 volts or 0 volts, that means the diode is leaky. It's not working properly. The diode is working, but it's not working to its proper efficiency or proper capacity. So even in this condition, the diode is bad. To check the HV capacitors, what we have to do is we have to simply touch both the terminals of the capacitor while keeping the multimeter at the highest resistance level possible. And then what the multimeter does is, initially it shows around 400 kilo ohms to 700 kilo ohms, and then in a few seconds it reaches 10 mega ohms when it discharges actually. So if the meter shows 10 mega ohms without the charging action, that is, it should charge initially. The charging action is shown when it is initially showing a resistance of 400 kilo ohms to 700 kilo ohms. But directly, if it shows 10 mega ohms, it indicates that the capacitor is open. For charging and discharging of the capacitor, initially the capacitor shows 400 kilo ohms to 700 kilo ohms, and then in a few seconds it discharges, and the capacitor across the capacitor the reading shows 10 mega ohms. If not, then it is faulty. To checking the capacitor for short, if it is internally short, when both the terminals are touched by the multimeter, then it will show 0 ohms, because if it is short internally, then the resistance is 0. It will show 0. If the capacitor is leaky, then it will show less than 10 mega ohms after discharge. So initially it will show 400 to 700 kilo ohms, and then after discharge, that is after a few seconds, it will not show 10 mega ohms, it will show a small value of the resistance which is less than 10 kilo ohms. Then we know that this capacitor is working, but it is not working to its full capacity and it is leaky. So leaky capacitor is also equally bad and it should be replaced. How to check whether the HV transformer is faulty? For testing the HV transformer, what we need is a multimeter, and we have to check the resistance at various places on the transformer. Here is how we will do it. We check the primary windings. Across the primary winding, the resistance would be 1 ohm to 1.5 ohms. That's all. A faulty condition is if the two leads of the primary winding, they show 0 ohms. That means somewhere the winding is short. Or if they show open, OL or infinity, then that means the winding is open. So for the filament winding, the secondary, there are two windings. One is the filament winding and the second winding is the step-up winding. For the filament winding, the resistance should be 0.5 ohms to 0.7 ohms. Very little resistance. The faulty condition again is for winding short it is 0 ohms and winding open it is infinity. Coming to the secondary winding, step-up winding. Step-up winding resistance should be 100 to 150 ohms. In the faulty condition again, the winding short will show 0 ohms and winding open will show infinity. Between primary and the core, select the highest resistance range in the meter and measure between primary winding and the core. The primary winding to secondary, if it is short, it will show 0 ohms. Primary to secondary leaky will show a certain value of resistance. Because primary and the secondary winding, it should not be short, neither it should be leaky. Checking between the filament winding and the core, again set the multimeter to the highest resistance value. Between the filament winding and the core, the primary to secondary short is 0 ohms, leaky is a certain value of resistance. And actually it should be infinity to indicate that it is a good transformer. Now to check whether the magnetron is faulty. This is the location of the magnetron. To check the magnetron which is faulty, we need a multimeter with the lowest resistance range in the meter. We have to set it in the lowest resistance range, and across the filament terminals of the multimeter, we have to check the resistance. It should be a very low value of resistance between 0.5 to 1 ohms. A faulty condition is 0 ohms if the filaments are short inside, and if the filaments are open, then it will show in. Again, testing the magnetron between the anode to the filament, set the multimeter to the highest range of resistance, and then measure between filament terminal and the anode of the magnetron body, that is the magnetron body and the filament terminal. Filament to anode, if it is short, if it is body short, that is, then it will give 0 ohms. If it is leaky, it will give a certain value of resistance. Ideally, the value should be infinity. Other problems that can occur with the magnetron are if the magnet is cracked, where it is shown over here with a red circle, and there is a mica filter paper which is placed just below or in front of the magnetron, and this paper, if it is broken or if it is burnt or if it is cracked, then also there is a problem of magnetron getting defective because of this. Check for cracks in the magnet, check for waveguide cover whether it is burnt or if it is browned or whether it is blackened or whether it is cracked or it is torn. So all this will indicate that there has been some kind of a misuse which has resulted in a damage. And then there is a golden colored gasket. If there are brown or blackened spots on it, you can be sure that there has been a reversal of microwaves from the cabinet into again the magnetron, which has rendered the magnetron faulty or it has burnt it in some way. This is due to microwaves reflecting back from the cabinet, and that happens when a metal container is used to cook food in the microwave mode. Any metal, that is, whether it could be stainless steel or it could be copper or any metal which reflects the magnetron waves. Another indication of a faulty magnetron is a blackened spot near the terminal cover, which would indicate that these terminals have somehow shorted from inside. Use of wrong utensils. Like I said, if metal utensils are used, what they will do is they will reflect the magnetic waves, waves from the magnetron, and these waves will again go back towards the magnetron and it can destroy the magnetron itself. These kind of sparks, and these sparks, they will destroy the oven cavity as well as the reflected waves. They will destroy the magnetron and burn it. So these are the various checkpoints when we check there is no cooking in the microwave oven. Thank you friends. See you later with another set of diagnosis.